Molecular emission spectroscopy. In molecular emission spectroscopy, the emitted radiation by material are measured with the help of machine known as spectrophotometer. Here you see this is the material solution which emit the radiation, and we put the detector in front of the emitted radiation. So in case of molecular emission spectroscopy, the emitted radiations are measured. Emission spectroscopy, this is a de-excitation process. What is meant by de-excitation process? So in emission spectroscopy, the excited electron, when they come back to the ground state, so it emits the extra energy in the form of light. Here again you see the excited in triplet state, this is singlet state, triplet state, and they come to the ground state. So the extra energy when they come back to the ground state, so they emit in the form of light, and that emitted radiation we are measuring with the help of the detector or spectrophotometer. So it is called emission spectroscopy. Luminescence, process in which molecule emit light from electronically excited state created by either physical, mechanical, or chemical mechanism. Types of luminescence: there are 6 types of luminescence: photoluminescence, chemoluminescence, bioluminescence, triboluminescence, cathodoluminescence, thermoluminescence. In photoluminescence, the excitation source is the light energy. In chemoluminescence, the excitation source is the chemical reaction. The electrons are excited with the help of chemical reaction. In bioluminescence, the excitation source is the biological system, just like firefly, glowworms, jellyfish. Triboluminescence, a release of energy when certain crystals such as sugar are broken down. Cathodoluminescence, energy of excitation is provided by the exposure of cathode rays. Thermoluminescence, when a material existing at higher vibrational energy levels emits energy at temperature below red heat after being exposed to small amount of thermal energy. Photoluminescence is further subdivided into fluorescence and phosphorescence. In case of fluorescence, the de-excitation is from singlet to singlet ground state, and here the emitted radiation in the form of light that we call fluorescence. While in case of phosphorescence, the excited state is triplet, from triplet to singlet. Fluorescence: at room temperature, most of molecules occupy the lowest vibrational level of the ground electronic state, and on absorption, visible or ultraviolet light, they are excited to excited state. The de-excitation of electron from the singlet to singlet ground state, along with the energy, along with the light, with the emission of light, is called fluorescence, as shown by the Jablonski diagram. This is the Jablonski diagram. Here you see this is 0, 1, 2, 3. This S0. This is, it shows the ground state. Okay, and here S1 and S2. These are excited state. Okay, so in where we are vibrational relaxation, non-radiation process, intersystem conversion, non-radiative process, ST, intersystem crossing, fluorescence, F fluorescence, and P phosphorescence. Phosphorescence, this is the de-excitation from a triplet excited state to the ground state along with the light. Here you see in this diagram you see 2 spectra. The first spectra, this is due to fluorescence, and the second one, this is due to phosphorescence. You know, in case of fluorescence, the de-excitation is from singlet to singlet knot, but in case of phosphorescence, the de-excitation is from triplet to S knot. Jablonski diagram. Here you see this is the Jablonski diagram. Here S naught, it shows the ground states S1, S2, and S3. These are the excited energy states. Here this is IC. Here you see this is IC and ISC. Where S stand for singlet state, T stand for triplet state, IC internal conversion, ISC intersystem crossing, R relaxation, F fluorescence, and P phosphorescence. What is meant by intersystem crossing? Here you see the electron is in the singlet form, and when the spin multiplicity is changed to the triplet, so then we call it intersystem crossing over. And when electron de-excite from the triplet excited state to the ground state, so the light the light energy we are getting in the form, and it is called phosphorescence. But when the de-excitation is from singlet to the ground S0 to the ground state, so then the light energy it is called fluorescence. And here you see IC, this is the relaxation of electron, and it's all the electrons when they are in S3 or S2. First they need to come down to the S1, to the lowest energy level, that is the excited state. So in case of the fluorescence, the de-excitation must be from S1 to the S0. The activation process: vibrational relaxation, internal conversion, external conversion, intersystem crossing, phosphorescence. Types of fluorescence and emission process. There are different types of fluorescence. Stock fluorescence. In case of stock fluorescence, emitted wavelength is greater than the excitation wavelength. Here you see this is the excitation, here this is the excitation, and here this is the emission. And the difference between this peak and this peak called stock difference, and this is here. So here you see in case of stock fluorescence, the emitted wavelength that is here, the emitted wavelength that is greater than the excitation wavelength. Anti-stock fluorescence: if thermal energy is added to an excited state, or a compound has many highly populated vibration energy level, emission at shorter wavelength than those of absorption occur. This is oftenly observed in dilute gases at high temperature. Resonance fluorescence: when the emitted wavelength is equal to the excitation wavelength. Here you see in resonant fluorescence, the emitted and absorbed radiation both are having the same energy or wavelength. This type of fluorescence is never observed in solution because of solvent interaction, but it does occur in gases and in crystal. It is also the basis of atomic fluorescence. Another type of fluorescence, Rayleigh Tyndall scattering. Incident radiation is not only absorbed or transmitted by the sample, but it is also scattered in all directions. The scattering takes place either from the molecules themselves, that is known as Rayleigh scattering, or from small particles in colloidal suspension, that is known as Tyndall scattering. Both types of scattering means the incident radiation is collected together with fluorescence emission intensity, and unless adequate precautions are taken to separate the fluorescence, inaccurate result will be obtained. Rayleigh-Tyndall scattering will limit the sensitivity of an assay where fluorescence takes place at wavelength close to the excitation wavelength, since total separation is impossible. Raman scattering: during the Rayleigh scattering process, some of the incident energy can be abstracted and converted into vibrational and rotational energy. The resulting energy scatter is therefore of lower energy and of longer wavelength than the incident radiation. The result is a weak emission which may interfere or be confused with the fluorescence of the sample. Since the amount of energy abstracted is always constant, Raman bands appear separated from the incident radiation by the same frequency difference, irrespective of the wavelength of the exciting light. If therefore the Raman band of the solvent coincide with the fluorescence emission of the solute, separation can be achieved by changing the excitation wavelength to a lower value. Hence the Raman band will also be lowered. Since the wavelength of fluorescence emission is independent of the exciting wavelength, the fluorescence will be separated from the Raman scatter. All solvent containing hydrogen atoms like to either carbon or oxygen show Raman band shifted approximately 3000 per centimeter from the exciting radiation. So in Raman scattering, you want to minimize what you have to do. You have to lower the excitation wavelength, okay, and so it will get change. Fluorescence efficiency or quantum yield of fluorescence. The fluorescence efficiency is equal to the number of photons emitted divided by the number of photons absorbed. One is the maximum fluorescence efficiency, that is the maximum one. And the higher the value of fluorescence efficiency, the greater of fluorescence of a compound. A non-fluorescent molecule is one whose quantum efficiency is zero or so close to zero, that is the fluorescence is not measurable. Fluorescence lifetime. Another important property of the fluorescence molecule is the lifetime of the lowest excited singlet states. The lifetime of excited singlet state is defined by the average time the molecule spends in the excited state prior to return to the ground state. Generally, fluorescence lifetimes are near 10 nanoseconds. The quantum yield of fluorescence and lifetimes are related by here. You see Kf divided by Kf plus Kd, where Kf into lifetime, where Kf is the rate of fluorescence, Kd is the radiationless rate of the deactivation. Fluorescence lifetime measurement is a valuable technique in the analysis of multi-component sample containing analyzed with overlapping fluorescence bands. Fluorescence related to concentration. The fraction of total beam of light absorbed by a sample is independent of the intensity of the incident beam. This is a very important point. It means the fraction of light absorbed by a sample is independent of the intensity of the incident beam and is related to the concentration of the absorption species by familiar Beer-Lambert law. Here you see I naught by I is equal to E exponent minus ECL. It is also written as log because natural log you have to convert to log to the base 10. I naught by I is equal to ECL, where I intensity of transmitted light, I naught is the intensity of incident light, E molecular extension coefficient, C is the concentration, 1 is path length of sample, and the quantity log to the base 10 I naught by I is equal to A is known as the absorption or optical density of the sample. So we can write it as here log to the base 10 I naught by I is equal to A, that is equal to emission intensity, and that is equal to ECL. The fluorescence emission intensity of weakly absorbing dilute sample is related to the molecular extent coefficient by the relationship fluorescence emission intensity is equal to I naught 2.303. This is the value of the E, and ECL, and here you see the fluorescence efficiency, and this is F. And so the fluorescence emission intensity is directly proportional to the intensity of the incident radiation, and fluorescence depend directly on the incident radiation intensity. These two equations explain the difference in sensitivity between absorption and fluorometric procedure. Sensitivity in absorption measurement is limited by the ability of the instrument to discriminate between the two nearly equal signals due to I and I naught, and the detection limit for even the most favorable cases rarely exceeds 10 raised to the power minus 8 moles. In case of fluorometric instrument are limited only by the intensity of exciting light and the ability to detect low light levels. So under ideal condition, concentration of 10 raised to power minus 12 moles can be measured. Factors affecting fluorescence intensity. Uh, there are two factors. One is intrinsic structure of a molecule. The second one is environment of a molecule. Intrinsic structure of a molecule. Okay, fluorescence is expected in a molecule that are aromatic or multiple conjugated double bonds. They are having multiple conjugated double bond or they are aromatic. So their fluorescence intensity is going to increase. In case of conjugation, here you see the double bond conjugation increase. So the unsaturation is going to increase, double bond is increasing. And when unsaturation is increasing, so the absorption of UV visible radiation will be increased, and it also increase the fluorescence intensity. But in case of aromatic, aliphatic, and alicyclic compounds, the number of rings are increased. As the number of rings are increased, so the fluorescence emission intensity will also increase. Nature of substitution group, we are having electron donating groups. Uh, so with increasing the number of electron donating group, the fluorescence intensity will increase. There is another electron withdrawing groups. So with increasing the number of electron withdrawing group, so the fluorescence intensity will go decrease. Here you see the arrow is getting is in the direction of decrease. Groups increase fluorescence intensity. NH2, OH, OMe, these groups, all these groups, they increase fluorescence, uh, uh, they increase the fluorescence intensity. The groups, they decrease the fluorescence intensity. COOH, CHO, COR. Groups have no effect on fluorescence intensity. SO3, H, NH4 plus alkyl group. Rigidity of the structure. Here you see this structure is flexible structure. Uh, uh, so the fluorescence intensity for the flexible structure will be less. Okay, and here you see this structure is rigid. You couldn't rotate this structure, but this structure can easily be rotated. So in case of rigid structure, the fluorescence intensity will be more. Heterocyclic compound, here you see pyridine, quinoline, isoquinoline. Here you see no fluorescence. Why? Because lone pair of electron enter triplet state by intersystem crossing. In all these compound, this is the system is converting from singlet to triplet, and when they convert into singlet to triplet, so the fluorescence, there will be no fluorescence. Environment of a molecule. A rise in temperature almost always accompanied by decrease in fluorescence intensity, because the greater fluorescence of collision between molecules increase the probability for deactivation by internal conversion and vibrational relaxation. So here you see temperature. When the temperature is going to increase, there will be more collision, and if there is more collision, so the fluorescence intensity will decrease. Viscosity, when you are going to increase the viscosity, so there will be more collision, the possibility for more collision, and here the possibility for more collision, so the fluorescence intensity will be decreased. Here it will be decreased. The arrow, this is a mistake, so the arrow will be, it will be going to decrease. Oxygen, dissolved oxygen often decrease the fluorescence intensity dramatically and is interference in many fluorometric methods. Molecular oxygen is paramagnetic, has triplet ground state, which promote intersystem crossing over from singlet to triplet state in other molecules. The longer lifetimes of the triplet state increase the opportunity for radiation less deactivation to occur. Other paramagnetic substances, including most transition metal, exhibit this same effect. Polarity of the solvent reduce the fluorescence intensity. Solvent affect fluorescence through their ability to stabilize ground and excited state differently, thereby increasing the solvent polarity, reducing fluorescence intensity. The effect of pH of a solution. Changing in pH influences the degree of ionization, which in turn may affect the extent of conjugation or the aromaticity of the compound. Phenols, acidic, undissociated, so no fluorescence. For alkaline substance, dissociated, good fluorescence. Anarine, acidic, fluorescence in visible region. Alkaline, neutral, fluorescence in UV. region. Photochemical decomposition, no fluorescence. To avoid this, choose wavelength not strongly absorbed. Absorption sensitive method to dilute solution are used. Light monochromator light is essential for excitation. Concentration of solution, here you see calibration curve. So in case of fluorescence, we need to use the dilute solution, not much concentrated, because here you see this is the deviation of Beer-Lambert law, because the fluorescence intensity and the concentration of solution is simply follow the Beer-Lambert law, and you know the limitation of Beer-Lambert law that is usually used for the dilute solution. Common problem of fluorescence measurements. Reference material is a fluorescence as the sample. Contaminating substance, Raman scattering, relaxed scattering. Fluorescence reading is not stable. Fogging of the cuvette when the contents are much colder than the ambient temperature. Drops of liquid on the external faces of the cuvette. Light passing through the meniscus of the sample. Bubbles forming in the solution as it is warm. Quencher, molecular oxygen sensitivity is inadequate. Problems with phospholuminescence, self-quenching, resonance energy transfer, self-absorption. Self-quenching result when luminescent molecules collide and lose their excitation energy by radiation transfer. Serious offender are impurity, dissolved oxygen, and heavy atoms are paramagnetic species. They are the sources for self-quenching. Resonance energy transfer. Sometimes quenching results from the transfer of energy to other acceptor molecules residing physically close to the exciting fluorochrome, a phenomenon known as a resonance energy transfer. It can be reduced by dilution, viewing the luminescence near in front surface of the cell, and using the method of standard addition for elevating sample. Self-absorption, attenuation of the existing radiation as it passes through the cell can be caused by too concentrated an analyte. The remedy is to dilute the sample and note whether the luminescence increase or decrease. If the luminescence increase upon sample dilution, one is working on the high concentration side of the luminescence maximum. This region should be avoided. Scalar formation. Formation of a complex between the excited molecule and another molecule in the ground state is called X-schema. Cause a problem when it dissociates with the emission of luminescent radiation at longer wavelength than the normal luminescence. Dilution help to less this effect. Photo-bleaching, sometimes termed as fading, is the photochemical alteration of a fluorophore molecule such that it primarily is unable to fluoresce. This is caused by splitting of coiling bond or non-specific reaction between the fluorophore and surrounding molecule. Such irreversible modification in covalent bond are caused by transition from a singlet state to the triplet state of the fluorophore. So photo-bleaching can be minimized by reducing exposure time or by lowering the excitation energy. However, these remedies are accompanied by the undesirable effect of reducing the chromophore fluorescence emission energy. Quenching, as we mentioned, which occur by reducing the fluorescence intensity by computing a process such as temperature, high oxygen concentration, and molecular aggregation in the presence of salt or halogen compound. Sometimes quenching results from the transfer of energy to other acceptor molecules residing physically close to excited fluorochrome, a phenomenon known as resonance energy transfer. This particular phenomenon has become the basis for a newer technique measuring distance far below the lateral resolution of the light microscope. Excitation spectrum and emission spectrum. Excitation spectrum is a measure of the ability of radiation to raise a molecule to various excited state at different wavelength. So an excitation spectrum is a recording of fluorescence is a recording of absorption versus the wavelength of the excitation. Okay, emission spectrum here. This is the recording or the curve which in which on one side we are taking the emission intensity and on the other side we are taking the excitation wavelength, the emission wavelength. As you can see here, this is excitation spectrum, and here you see this is the emission spectrum. Okay, so here the excitation wavelength is here. On this side we are taking intensity, on this side we are taking the wavelength. And these two are the mirror images of each other. Instrumentation for fluorescence spectroscopy. Here this is the light source, this is the slit, this is the monochromator which converts the polychromatic light into monochromatic, and yes, here will be the sample holder. Okay, and here there will be the emission monochromator, the slit and emission monochromator, and here we put the detector, and here is the data recorder or data processor. From here you can see light source, excitation monochromator, sample holder, emission monochromator, and here is the detector. Light source gets charge lamp as in an arc lamp. Wavelength selection, filters or monochromators, grating or prism. Sample compartment fluorescence cells. Here you see quartz or fused silica. Detectors, photomultiplier, photoconductive target, Vidicom. Applications, direct measurement, metal cation as a fluorescence chelates. Indirect measurement, where the fluorescence of the substance being determined is measured prior to and after quenching. Indirect measurement, where the fluorescence of the determined substance is enhanced by the addition of a reacting material. Tracer techniques, by engineered analysis, and spectrofluorescence signatures. Thank you.